Alright, so in today's video, I wanted to go ahead and go over the attributes of polynomial functions. Before we get into the graphing part of this worksheet, let's go ahead and talk about this top piece right here. It says a polynomial function is a function of this form right here. Please don't forget, whenever you see f of x, that is the same thing as y. And it's written in this form, but we have seen examples of these, and I'll give you one in just a moment. But here, a polynomial is where all coefficients are real numbers, all the exponents are whole numbers, and n is a positive integer. So notice here, the n is referring to the exponent. So here we gotta make sure the exponents are positive. And they cannot be negative. Okay. All right. And we'll start off with an example, but here it says the degree of a polynomial function is the value of the greatest exponent, or we can say the highest exponent. So let me give you an example of one, and I'll do this off to the side. So an example of a polynomial function would be f of x. Once again, this is just random. 3x to the fourth minus 2x cubed plus 2x plus 5. Here, if they ever ask for the degree of this polynomial function, we're going to look at the term with the highest exponent. If you notice here, this has a 3. This would have an exponent of 1. This doesn't have a term attached to it. So really the highest exponent would be this right here, 4. So this polynomial function we'll call a degree 4 polynomial because of this exponent right here. If they ever ask for the leading term of this polynomial, the leading term is a term with the highest exponent. So once again, here it's in the front. So the leading term would be this whole thing, 3x to the fourth. Now if they ever ask for the leading coefficient, and I'll abbreviate that. The leading coefficient would be the number in front of our term. So the leading coefficient here would be 3. Okay. So once again, the degree of this polynomial is 4, the highest exponent. Our leading term is 3x to the fourth, and our leading coefficient is 3. So that will be very important in the near future. But let's go ahead and talk about these graphs right here. Here they call them the polynomial parent functions. And we're going to go ahead and use Desmos to help us figure out how each of these graphs look like. So for the constant function, the general form of a constant function is going to be f of x equals c, which is some number. So here we'll start off with a specific example. Let's just say f of x equals 5. Once again, we could just say y equals 5. F of x and y are the same thing. So if I go to Desmos and I type in, you can either type in f of x or y. If let's just say I type in y equals 5, it'll give me a horizontal line at 5. So here, once again, this is just a general function. But here, we know that if we're dealing with a constant function, it will be some horizontal line at whatever that c value is. Okay. So here we have a horizontal line. And notice here they refer to the degree of a constant function as 0. So if you wanted to be real technical, we can say for this piece, f of x equals 5, x raised to the 0 power. That's why they call this a degree 0 polynomial, because anything to the 0 power is just 1, and we're just left back with the 5. All right, we'll go ahead and graph this next one, the linear function, which is a function you should have also seen back in Algebra 1, f of x equals x. Don't forget here, the power is 1. So the degree of this is 1. If you graph it on decimals, it'll look something like this. Okay. And notice here, we intersect the x-axis at this point right here. So it intersects the x-axis. And it goes through it. Okay. Right. And one thing I want you to also be noticing is end behavior. Think about what happens as you go all the way to the left. Here we'll go down to the left. If you go all the way to the right, we'll go up and to the right. So I want you to be thinking about those ideas. Next one is the quadratic function. We've seen this before. Here, the general function is f of x equals x squared. The degree of this is 2 because our exponent is 2. And that looks something like this. And once again, here is one very important thing I want you to look at. But here, it'll intersect the x-axis only once. But here, it sort of bounces off the x-axis. So here we still hit the x-axis, but it bounces off. It doesn't intersect like the linear function does. And that's one idea I want you to think about. And here we think about end behavior. Both of these arrows are going up. Okay. So I want you to think about that. All right, let's go ahead and go over to the cubic. The cubic we talked about as well. F of x equals x cubed is the parent function. This is a degree 3 because our exponent is 3. And we said a while back, it'll look something like this. You can remember, you can graph these on decimals. Okay. All right. And if you look at this, the middle, we do intersect the x-axis, but we do it in a curved like manner. So here we do intersect it, but it's sort of curved when we intersect the x-axis. So there's this curvature present when we intersect the x-axis. And once again here, let's think about end behavior. This goes down to the left and then up and to the right. Notice here our degree is odd. This is an odd degree. And I want you to compare that to the linear function, which is also an odd degree. And I really want you to think about the similarities between them. So both do intersect the x-axis. And if you think about the end behaviors, I want you to think about how similar they are to each other. Okay. All right, let's go over to the quartic. So the quartic here, f of x is equal to x to the 4th. If I graph that on decimals, once again, we can say y equals x to the 4th. Notice here, it looks sort of like a quadratic. The only thing is when you get closer to the x-axis, it sort of flattens out. It still bounces off the x-axis, but it's a lot more flatter. So here, you gotta make sure you make that clear. It sort of looks like the quadratic, but it becomes more flatter once you get the x-axis. Okay. So here, once again, it does bounce off the x-axis, but when it does bounce off, the curve becomes more flatter. Okay. And if you compare this quartic to the quadratic, this is an even degree polynomial. You can also think about the end behavior. If you compare that to the quadratic, which also has an even degree polynomial, I really want you to think about end behavior and how they're related, and how they intersect the x-axis. Quadratic bounced off, and the quartic did as well. All right, and the last graph is the quintic. So here, the general parent function is f of x equals x to the 5th. If we graph that on decimals, I'll change that to a 5. And if you look at this one, this sort of looks like the cubic graph, just slightly different. Here we intersect the x-axis, we go through it, but just like the previous example, it sort of flattens out when we intersect the x-axis. So this, once again, looks like the cubic graph, but when we intersect the x-axis, it'll become more flatter. So you gotta make sure you make it clear. So it looks something like this, something like that. And remember, this is just a sketch. Okay. And once we get here, we intersect the x-axis. Here in a curved-like path, curved-like manner, but it does get more flatter when it intersects. Okay. And here, once again, this degree is odd. So I want you to be thinking about how that relates to the graph of the cubic function. Very similar. All right, so now let's talk about the graphing portion of this worksheet, and specifically talk about turning points. So here they say that turning points are the points at which the polynomial function switches direction. If you look at the little graph they give you, whenever we read a graph, we always want to read it from left to right. So here in this graph, we'll start off from the left. As we go from the left, we go up, up, up. We're increasing. Our function is increasing, 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 up until this point right here. And then we start to decrease, 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 up until we hit this point right here. After this point, we start to increase, 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 and we're always increasing after that. Okay. So let's go ahead and define these points. These are real special points. So once again, left to right, we're increasing here in this piece. We're increasing. And then after that, it starts to decrease, 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 up until the other point. So when the function changes from increasing to decreasing, we'll call this point a relative maximum. So here, we'll fill this in. We'll call that a relative maximum. And this, once again, occurs when your function goes from increasing to decreasing. All right, we get one other point as well. This point on the bottom. So once again, that's right, we're decreasing, decreasing, decreasing. After this point, we're always going to increase after that. So So in this last piece, we're increasing. So we would categorize this point as a relative minimum because our function goes from decreasing to increasing. So here we'll fill this in. We'll have a relative minimum when our function goes from decreasing to increasing. Both of these points right here, relative maximum, relative minimum, are also known as extrema. Extrema. Or they also be called relative extrema. And here, turning points define where a function is increasing or decreasing, which is what we just mentioned right here. So here it's very important to recognize when you have a relative maximum or a relative minimum. Okay. All right, so let's go into the graphing portion of these. I'm going to go ahead and go over 2 examples on this page right here. And I'll walk you through it using decimals. But here, I know they want you to use the calculator, but decimals is the best tool to use here to help us visualize the graph. It'll make us, allow us to analyze the data a little bit more smoothly. But the most important thing here for this worksheet is I do want you to round to 2 decimal places. If you end up getting decimals, which you will in some of the problems. Okay. So I need more space in this, so what we're going to go ahead and do is we're going to go over these 2 examples right here. And I'll walk you through them. So here, what they want you to do is graph each polynomial function using a table, which we'll get from decimals. And then they want you to list out the attributes, the domain, range, the turning points, where the function is increasing and decreasing, and what those intervals are, and behavior. And we'll talk about that right now. But here, you definitely want to make sure you graph this on decimals. So I'm going to go ahead and graph this on decimals. For this one, I'm going to put f of x. It doesn't matter, but I'm going to put f of x equals x cubed minus 3x squared minus 3. And once again, just be real careful when you're typing these in. We can zoom out a little bit. Okay. And the graph looks something like this right here. Okay. So we're going to go ahead and sketch that on our graph that it gave us. But here, there is a settings, a gear icon up here. If you click on that gear icon, there should be a little table icon that pops up. If you click on that table icon right there, it should give you a list of points on the graph that we'll go ahead and use to graph on our own graph. So here they give you -1, -7, 0, -3, 1, -5, 2, -7. So we can go ahead and plot those points onto our graph. I'm going to go ahead and take a picture of this and use that as a reference over here. Okay. So once again, -1, -7, -1, 1, 2, 3, 4, 5, 6, 7. 0, -3. 0, 1, 2, 3. 1, -5. 2, 3, 4, 5. 2, -7. Okay. And then here, what's really helpful is you definitely want some other point as well. I normally look at the x-axis. Decimals will give you that as well, where it intersects the x-axis. So that x value would also be another point as well. So 3.27, 0, we could just approximate that. It'll be somewhere 1, 2, 3, somewhere right after the 3. That's when it intersects the x-axis. So here we'll kind of follow this same shape from Desmos to help us up. And then here we're increasing. Then we turn, go back down, decreasing. Now we're increasing all the way through. We cross the x-axis, and it goes all the way up like that. Okay. So just make sure you do have the sketch right there. Okay. So now let's think about the domain and the range of this graph. One thing I want you to really notice is if you look at the leading term of this polynomial, which is x cubed, we said a while back that x cubed looks something like this. And we said that the domain and the range was all real numbers, or x cubed. So when you look back at our notes, but here, the end behavior, which is related to the domain and range here, both domain and range will be all real numbers. We can also write that as negative infinity to positive infinity for both. All right, so let's talk about relative maximum and relative minimum. And let's see where those are located. So once again, you always want to read the graph from left to right. Here in this piece, starting from the left, we're increasing. So that piece is increasing. And then we start to decrease in between. But then after that, we start to increase all the way through. Okay. So here, once again, we'll have a relative maximum when our function goes from increasing to decreasing. So here, going from the left, we go from increasing to decreasing. That means that this point right here is our relative maximum. Right? And we can find this relative maximum, which is a coordinate point, looking at Desmos, or you can just look at this graph. This point would be 0, -3. But once again, you can always verify that on Desmos. And of course, it is 0, -3. So we have a relative maximum at 0, -3. Okay. Always double check if you have multiple relative maximums. But if you look at the graph here, on the next page, we go from decreasing to increasing, and that's pretty much it. This will lead to another point that we'll look at right now. So we're done with relative maximum. Let's talk about relative minimum. Once again, this occurs only when your function goes from decreasing to increasing. So here we go from decreasing to increasing. Therefore, this point on the bottom right here is our relative minimum. And once again here, it appears that it's at 2, -7. Once again, you can always verify that on Desmos. And of course, that point is on there. So 2, -7. Okay. And we don't have any more relative minimum, so we're good. So we already classified the relative extrema. We're good. Now here, this next part does get a little confusing sometimes, but here they want you to tell us on what intervals the function is increasing or decreasing. Here we're thinking about the domain on which this occurs. So here we've sort of already categorized where this function is increasing. We know that in these pink pieces we're increasing. So we're thinking about domain here, starting from the left, we're going down to the left. So we're coming from the left. So our increasing portion of this graph will start off from negative infinity. And we're going up, 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 up to the x value of 0. Okay. And then now we start to decrease. We'll talk about this piece right now. But the other place where it does increase is starting from here all the way up. So here we got to think about the x value at this point. The x value here is 2. So here it'll also increase from 2. And then go all the way up and to the right to positive infinity. Don't forget that when we have two different intervals, we put a union symbol in between. So this is where the function is increasing on this domain. All right, let's talk about decreasing intervals. We know that in between here it's decreasing. And once again, we're focusing on the x values. So here, our x value is 0. So we'll go from 0, comma, and then we end up at what x value? Well, this x value is going to be 2. So in between 0 and 2, this function is decreasing. All right. Now let's talk about end behavior. This idea we have talked about in the past, but we have to come back to it. Here, if you read this first part, this says as x approaches negative infinity, so as it approaches the left side of the graph, the question here is, what are the y values approaching? What are they approaching? So as you go towards the left-hand side, we're going down and to the left, down and to the left. Our x values are approaching negative infinity, and our y values are also approaching negative infinity. So here, as x approaches negative infinity, our y values are approaching negative infinity. Same for this one as well. As x approaches the right-hand side, what are the y values approaching? So here, as we go towards the right-hand side, we're going up into the right. X values are approaching positive infinity. Y values are also approaching a positive infinity. So here, as x heads towards the right-hand side, as x approaches infinity, our y values are also approaching infinity. Okay. So these are definitely ideas I want you to be thinking about. Notice here, though, we do have a lot more nicer numbers to work with. In the next example, we'll be dealing with decimals, but we cover the same concepts here in this next example. So the last example I'll go ahead and go over for today is number 2. Be real careful with this one. But once you get here, now they're giving us a different function to work with. So I'm going to go ahead and do the same thing we did. They want you to graph it and list out the attributes of this polynomial. So I'll go ahead and go to decimals. I'll erase all this. And I'll go ahead and graph that new polynomial. So we have x to the 4th plus x cubed minus 4x squared, and then plus 5. So this graph does look a little weird, but here, once again, we can click the gear icon on decimals, hit the table icon. It'll give us a good list of points to work with. So here, let's go ahead and plot these points on decimals. And one thing, though, I want you to see here is these points that are highlighted are not really the most important points, but here, notice I had to sort of zoom in a little more to see this lower point. And then if you do the same for this other piece as well on the top right, you do have to go just zoom in a little more to see the actual point there. So be real careful with that. But for now, I'll use these nice points that they gave me for now. So I'll take a picture of this. Okay. So -2, -3. -1, 1. 0, we're at 5. 1, 2, 3, 4, 5. And at 1, we're at 3. 1, 2, 3. Okay. So let's go ahead and sketch this. So it appears that as you go to the left, we're going up. And then here, it sort of dips down a little more, and then it goes up, 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 up. Up until you hit this point right here. So we're increasing. Now we're decreasing, decreasing, decreasing. And then here goes just a little more down. So let me fix that. Goes just a little more down, and then it starts to increase all the way down. Okay. So the graph looks something like this. And we'll analyze that right now. But here, if you notice, the leading term is x to the 4th. If you look back at those little polynomial parent functions, x to the 4th is a quartic. Focus on the end behavior. It looks something like this at the end of the day. So notice here, both arrows are pointing up. Okay, so that is one thing I want you to be thinking about. But here we'll do the same thing. Domain and range. So the domain here would be the x values go all the way up and to the left. X values here approach -infinity. And then if you go to the right, up and to the right, the x values approach +infinity. So here the domain would be all real numbers, or -infinity to +infinity. The range would be a little bit different here, so be careful. For range, we think about the lowest y value. Here you got to be real careful. If you look at this graph, the lowest y value is actually located right here at this point. And that point, once again, we can go back to decimals and look at that lowest point would be right here. It tells us it's -1.83, comma -3.3. So once again, for these, if you ever get decimals, I want you to round to 2 decimal places. But here, the y value is -3.30966. So here, we'll round that to about -3.31 for the y value here. So for the range, we can say that y must be greater than or equal to -3.31. Since that is our lowest y value, anything above that would work for a range. Okay. All right, let's talk about relative maximum minimum. And once again, if you look at the graph, reading it from left to right, we're decreasing, decreasing, decreasing up until this point in the bottom. So here we're decreasing. Then we start to increase, increase, increase in between. In between, we decrease, decrease up until this point right here. Decreasing, and then after this, now we're increasing all the way. So now we have all the pieces we need to categorize our relative extrema. So for the relative maximum, once again, this occurs when your function goes from increasing to decreasing. Here in this point, this would not be considered a relative maximum, but if you look at this next piece, we go increasing, increasing, and then we change to decreasing. So here in this point, our relative maximum will be located at this point. which is 0, 5. We don't have any other points where it's a relative max, so we're good there. Now for the relative minimum, once again, you want to make sure you take into account all of these pieces. Once again, this is a relative max. I'll abbreviate it as that. But here now, if you look at this point at the very bottom, we go from decreasing to increasing. So this point would be a relative minimum, or relative min. And once again, we can look at that point again. Our relative minimum is right there. Negative 1.83, negative 3.309. We can round those two numbers to 2 decimal places. And if you do that, the coordinate point for that point would be negative 1.84 and comma negative 3.31. And here, don't forget, we have to check to see if there's any other relative minimum. So here, there is actually one more point we got to look at. In between here, we go from decreasing and then to increasing. So this right here would be a relative minimum as well. So that point we can get off with decimals. And if you look at that, we zoom in, that point is actually right there. 1.08, 2.95. If you round those to 2 decimal places, we'll go ahead and get 1.09, sorry, 1.09, comma, 2.95. Let me just double check that. Yep. So there you go. Here, in this case, we get 2 relative minimums. All right, let's talk about the domain on which the functions are increasing or decreasing. So here, for increasing, we know that in between here, we're increasing, as well as up here. So here, once again, we want to focus on the x values. Here, the x value would be starting from here. And this is just a little bit, you gotta be real careful with this one, but here, that x value was negative 1.84. So we're increasing from negative 1.84 all the way up to the x value right here, which is 0. And then we start to increase it again from this point right there, which was at 1.09. And then we start to increase all the way up and to the right. It keeps on going, so to positive infinity. Don't forget we put a union in between. The same for the decreasing intervals. Here, for decreasing, we start from the left, from negative infinity. All the way up to this x value, which is once again negative 1.84. And then we start to increase in between. So from 0 to 1.09. And once again, because we're thinking about intervals here, we'll put a union in between. All right, and that takes care of our increasing and decreasing intervals. Now let's talk about the end behavior. Once again, here, as x approaches the left-hand side, what are the y values approaching? So as you go to the left-hand side, our x values are approaching negative infinity, but the y values are actually going up towards positive infinity. So here we'll put positive infinity. Same for this last one. As x approaches the right-hand side, our x values are approaching infinity, and the y values are going up to positive infinity. So here, it'd be positive infinity. All right, so that pretty much wraps up the graphing portion of these. Once again, the most important thing is being able to graph these using decimals at this point and list out the attributes. Be real careful with the decimal places. All right. I'm going to go ahead and post the answers to the rest of these on Canvas. I highly recommend you work on these, but I do want you to make sure that you have these notes done before next class. Okay.